All right, so let's address a curious question, I suppose, which is, can a pair of police officers determine if you've been speeding using only a stopwatch and a walkie-talkie? That may be a strange question to ask, but the answer is yes, and in fact, well, it doesn't require police officers for that matter. Can any pair of people determine if a car has been speeding using only a stopwatch and a walkie-talkie? The answer to that is yes. But what's interesting and why the police officers come into play, can you get a ticket from police officers who have determined you're speeding using only a stopwatch and a walkie-talkie? The answer is in some states, yes. Depending on the laws. I believe Texas is a state where this is possible, and it may seem like a strange thing because you might think that a police officer might have to have a radar detector to be able to tell exactly how fast you're going, yet there's a way to do it with just a stopwatch and a walkie-talkie. So then the question might follow up with is how? So police officers can do this, okay, fine, it's on the books legally in some states. How can law possibly be written that you could pull somebody over with a stopwatch? So here's the thing to think about. You're traveling down the road in a car. Imagine this graph here is going to capture where you are at any moment in time. And here's the thing. At some moment in time, you are at a moment in time where the first cop records where you are at. So here is a moment in time, and here is where you are at. And the cop knows that you're there because the cop is sitting there with a stopwatch and he records, he knows where his position is, and he starts the clock to know where you're at. And now, you need a pair of police officers because there has to be another cop at another location. And that other cop is going to know when you got to that position, because when you got to that position where he's at, he's going to know by virtue of the stopwatch rolling. So, at some point of time in the future, you pass the other cop. The other cop is at some other location. So here is a passage through time from when the first cop saw you to when the second cop saw you. Here is a passage through space from where you were when the first cop saw you to where you were when the second cop saw you, and as you proceed along. And my claim is that with this information alone, where you were at time A, where you were at time B, let's call it F of A and F of B, the cop can know something about your speed. Here's the thing. If we're describing position and we're describing time, in order to describe speed, we're going to need that position divided by time. And since the cops only have these two increments of time, let us compute the average rate of change between those 2 points. Here is the change in y, here is the change in x. This is merely an average rate of change. This is precisely the slope of the line between the 2 points. So this here is the slope of the dashed line. Now, here's the question. How can the cop possibly be able to pull you over based on the slope of the dashed line? Well, the cop knows your average speed. Say your average speed was faster than the speed limit. Maybe when you passed the first cop, you were going at the speed limit. And when you passed the second cop, you were going at the speed limit. However, if your average speed between passing the first cop and passing the second cop was a rate that would be faster than the speed limit, well, the fact that you passed them going the speed limit has nothing to do with it. At some point, if you pass them at the speed limit, but your average speed is above the speed limit, you must have been going above the speed limit at some point. And specifically, if you think about this, because no matter how you fill in the graph here from one point to the other, let me fill in the graph like imagine you pass the one cop going at a low rate of speed, and imagine you pass the other cop at another relatively low rate of speed. You can see like this flat slope corresponding to a relatively low rate of speed whenever you came to each cop. But the fact of the matter is, since your average speed is this dashed line, and you can see it if you look, there are a couple points along this curve where your instantaneous speed, your tangent line, would have the same slope as that average speed. Here, the tangent line has the same slope as the average speed. So the long story short is, if your average speed was what it was, even if you passed both cops going very slowly, well, based on some property of functions, which we're going to describe in the next video, there must have been at least some point along the way where your speedometer at that point, at that instant, read at the speed of the dashed line. And how could we characterize that mathematically? Well, this point that we're looking at here, let's call it time c. The idea is, at time c, the slope of the tangent line is equal to the slope of the secant line between the 2 points where the cops measured. So here's the average rate of change, the change in y over the change in x of the dashed black line. But what now is the slope of the dashed blue line? The slope of the dashed blue line is the derivative at the point C. So I'm going to put this in a box, and we're going to talk more about this in the next video. But the long story short is, the idea behind this is something that is of pivotal importance to calculus, and something that's, something every first semester calculus student sees. So let's talk about that in the next video.